Hi, welcome back. We're in Lecture 8, Segment 2. The topic of this lecture is Null Hypothesis Significance Testing, for short, NHST. In the first segment, I gave you an overview of how NHST works. Now, in this segment, I'm going to get into the more controversial aspects of NHST. I'm going to list several problems that critics of NHST are quick to point out, but I'll also note some remedies that you can supplement your NHSTs with to overcome some of these problems. So there are several problems with NHST, and I've listed just 6 here. Hardcore critics of NHST would probably list more, but I just listed what I think to be the 6 primary problems with NHST. I'll go through each of these in turn, and then after I go through the problems, I'll talk about ways to overcome those problems, what I call the remedies. So let's just go through the list. The first problem is that it's biased by sample size. So we've already seen this in action if you looked at your R output and your p-values as they relate to sample size. So for example, in regression, the p-value that you get in your R output is based on the t-value that's calculated, and the t-value in regression is the unstandardized regression coefficient b divided by standard error, where standard error is the square root of the sum of squares residual divided by sample size minus 2. Okay, we went through these calculations as we talked about regression. You can verify them by looking in your R output. The important thing to notice here is n is in the denominator of the standard error equation, and standard error is in the denominator of the t equation. So here's n. Imagine that I just jack up n really, really high. Imagine I get a huge sample of thousands of people. If n goes really, really high, then standard error is going to go really low. If standard error goes really low, then the t-value is going to go very high. And a high t-value is always going to be associated with a very low p-value, which would allow you to reject the null hypothesis. So regardless of what the actual slope is, regardless of what b is, if I just increase n to an astronomical number, then I'll get a very low standard error. In turn, I'll get a very high t-value, and in turn, I'll get a very low p-value, which will allow me to reject the null hypothesis every time. That's what statisticians mean when they say NHST is biased by sample size. We'll get a significant result almost all the time if we just obtain a really large sample. The second problem is this arbitrary decision rule. Right? We just have to pick some cutoff value and say, once I get to that value, I'm going to reject the null hypothesis. Now, it's become standard, particularly in the social sciences, particularly in psychology, that an alpha value of 0.05 or p less than 0.05 indicates that you can reject the null hypothesis and claim that you have a statistically significant effect. But that's completely arbitrary. That's just we just somehow landed on p less than 0.05 as a field. We could change that to 0.01 if we wanted to be more conservative. We could change it to 0.1 if we wanted to be more liberal. The point is that it's completely arbitrary. So that's what I mean by arbitrary decision rule. On top of that, problems arise, and some sort of funny problems arise in the literature, in the scientific literature, when p-values come close to 0.05. It's funny how authors will twist and turn their language when they get a p of 0.06. It's trending towards significance. It's marginally significant. It's almost there. They'll almost always report the result as if it's significant if the p-value gets close enough to 0.05, which is really violating the rules of the game, right? It has to be this binary decision, reject, retain, only if your obtained p-value is less than your specified alpha value. But people don't do that in reality, especially when they're writing up results for scientific journals. This third problem I came up with sort of a funny name for, so forgive me, the yokel local test. What I mean by that is that's sort of a phrase for, it's just sort of what you do as a common custom. So a lot of people, even really good researchers who have PhDs and are doing cutting edge research, even those people sometimes just do NHSTs because it's the only thing they ever learned. They took one statistics course in graduate school on their way to a PhD, and they learned how to do an NHST, and then that's it. They learned P less than 0.05 means statistically significant, and that's how they conduct their research. So that's what I mean by yokel local. It's just the custom, and it's the only thing you've learned, and that's your reason for doing it. And as we know, that's never a good reason for choosing one procedure over another or choosing one tool over another in science. Just because it's the one that you know and it's the only one you know isn't the reason why you should go with it. So one, this is a problem because it's the only thing that some people know, and in turn it encourages weak hypothesis testing. Remember, if you set up the rules of the game, it's just nothing will happen, the null hypothesis, or something will happen. Well, that's not a very strong form of hypothesis testing. So if you only know this one way of doing things, then it encourages weak hypothesis testing, sort of weak thinking in terms of testing theories in science. The next problem is we know it's error prone, right? So from the last segment, we know that there's always a possibility of type 1 errors and type 2 errors. And it's actually worse than I outlined in the last segment. So the probability of type 1 errors actually increases and can get really high as researchers conduct multiple tests, especially multiple tests on the same data. These are called dependent tests. If you don't correct for the multiple tests, then that probability of a type 1 error just keeps compounding and inflating. So the probability of type 1 error can be really inflated if researchers aren't careful. On the flip side, there are a lot of fields of research, especially in the social sciences and especially psychology, that are just plagued with a large degree of sampling error. We have big populations but don't have a lot of resources to obtain big samples, so we get small samples relative to these big populations, which gives us a large amount of sampling error, big estimates of standard error, which means we're going to wind up missing a lot of effects, even if they really exist out there in the population. So not only is it error prone, we know we have a certain probability of getting type 1 and type 2 errors, but in a lot of fields of research, it's actually worse than I outlined in the first segment. And finally, NHST forces you to engage in what I call shady logic. And at first, it seems very clear. So if you remember from basic logic class, modus tollens, everything on this slide is perfectly valid. So modus tollens just says, if P then Q, not Q, therefore not P. That's all valid. It would be valid if we said exactly that. If the null hypothesis is correct, right, we assume the null to be true. So if the null is correct, then these data that I obtain in my experiment cannot occur. The data have occurred, therefore the null hypothesis is false. That's exactly modus tollens, that's all valid. But unfortunately, that's not how we do it. The problem is that the logic becomes probabilistic in NHST and in inferential statistics. So instead, this is how it goes. If the null hypothesis is correct, that's the assumption we make, then these data are highly unlikely. That's the probabilistic part. These data have occurred. Therefore, the null hypothesis is highly unlikely. That's what we do when we engage in NHST. But let's take it out of NHST and use just an everyday example. So if a person plays football, then he or she is probably not a professional player. That's true. A very small percentage of people go on to play professional football, right? I wish I could have. I tried. I played in college, didn't make it. So I didn't go pro like most people. So if a person plays football, then he or she is probably not a professional player. But wait, this person is a professional player. Therefore, he or she probably does not play football. What? That doesn't make any sense. But if you compare these two logic outcomes, the first one and the second one, they're exactly the same. The problem going from the last slide to this slide is that we made it probabilistic. And once you do that, you engage in what's called shady logic. And you come to some pretty odd conclusions like this one down at the bottom. So given all those problems, why do we still use it at all? Well, there are a lot of people out there who would say we shouldn't be using it. We should ban NHST and this reliance on p-values. I'm not so strict about that. I think there are several remedies that you can add to your research that will ameliorate a lot of those problems. And just being educated about what NHST does and doesn't do is a huge step of the way there. So if you understand this segment or this entire lecture, then hopefully you won't make the mistakes that some people make when interpreting p-values and the idea of statistically significant. So first, let's go back through the problems. So bias by sample size. A simple thing to do, and this is common now in most peer-reviewed journals, is whenever you report an NHST, also report estimates of effect size. Because effect size tell you not just if an effect is significant or not, but it tells you about the magnitude of the effect. So for example, in regression, we'll report standardized regression coefficients and the model R-squared. That tells us about the magnitude of effects. Same holds for this arbitrary decision rule. So yeah, it's arbitrary, but if you're right on the cusp, then don't worry so much about being significant or not significant. Report estimates of effect size. That'll tell people whether you have a large effect or a small effect. With respect to this yokel-local test, obviously go out and learn other forms of hypothesis testing. And second, consider adding in multiple alternative hypotheses. You don't have to have just the null and one alternative. You could have the null, alternative 1, alternative 2, and so on, and then engage in model comparison, which we'll do next week when we do multiple regression. In terms of the tests being error-prone, there are several steps we can take to protect against the impact of those errors. So, number one, most importantly, replicate significant effects to avoid the long-term impact of type 1 errors. So, for example, go back to lecture 1 when we talked about the effect of working memory training on intelligence. Those authors found that there was a significant effect, right? But that might have been a type 1 error. So we need to replicate that effect over and over again so that the entire literature and society at large doesn't start to believe that that's a real result. So significant effects need to be replicated to avoid long-term impact of type 1 errors. To avoid type 2 errors, simply obtain large, random representative samples. That'll give you a shot at obtaining an effect if it exists in the population. With respect to the shady logic, there's no way out of that one, except to say, remember what a p-value is. And when I teach this course at Princeton, this is perhaps the one thing that I tell them. If you walk out of this classroom and away from Princeton University, please remember this one thing that you learned from statistics, that what this p-value means. It's the probability of obtaining these data or data more extreme given the assumption that the null hypothesis is true. If you just remember that, then you won't engage in that shady logic. Now, if that's not enough for you, then you might want to just avoid NHST altogether. There are alternatives. One option is just to report confidence intervals only, and I'll show you how to do that in lecture 10, or engage in another form of hypothesis testing called Bayesian inference. And that's really beyond the scope of this course, but it's an approach that's very powerful and becoming more popular in statistics, even in introductory level statistics, which is why, as I wrap up this segment, you look at my 6 problems, you'll see they make up the acronym Bayes. And that's the end of this segment.